Global optimization, in previous topics we have seen image is processed by pixel or part of the image is processed as the pyramids and so and so. In this global optimization, the processing is done for the whole image rather than doing it pixel by pixel. That's what mentioned in the first point. So instead of applying the filters directly, we are going to define a goal for desired transformation, and then we are going to find the solution that best satisfy the goal. We generally know the optimization means finding the best solution, not just finding the solution is enough. We have to find the best solution among it. So this process is to find the best solution that satisfy the goal. So this is mainly achieved using the smoothness across the entire image. So two approaches to be followed. One is regularization, another one is Bayesian formulation. Here we are going to see about regularization. We will build a global energy function that will describe the entire image properties. The minimum energy solution is required, that is done using the sparse linear system or iterative optimization methods. So don't worry about it. The entire regularization is about determining the energy function. That's what mentioned here. We are going to determine the energy function. First I'll tell you the general term and then I'll make it division of the process. So you have to keep in mind the equation E equal to ED plus lambda into ES. So this E is total energy, this A is total energy, and ED represents the data energy, and ES represents smoothness energy. ES represents smoothness energy, and lambda is nothing but trade-off factor. So ED, data term, ED is nothing but data term. This represents how well the solution fits the observed data. ED represents how well the solution fits the observed data. ES is a smoothness term. It represents how smooth or natural the image is. So this lambda is trade-off. If the trade-off is high, if the lambda value is high, then the image is much better smoother. If the lambda value is low lambda represents good fit of data than smoothness. So both the data and smoothness is inversely proportional. High data means high smoothness, low data fitting. Low lambda means a good fit in data but it is less smooth. And in general the total energy represents it can be of higher as well as lower. Lower energy is better. So we have to minimize the energy to get the better result of image. So high means worse solution. So that's what mentioned in the beginning. We are going to build a global energy function and we are going to find the minimum energy solution. Minimum energy solution is required. So why we need to learn this concept? So this kind of regularization is mostly suitable for denoising an image, as well as it can be used for segmentation purpose, segmentation of images. So in this kind of application we need to find a good image. Okay, so in such case we have to focus on both data as well as smoothness. So there comes the regularization. So regularization is a technique used in global optimization to avoid noisy solution or to avoid overfitting. It imposes a smoothness, prior or other constraints. So it is developed by statisticians for solving ill-posed problem. Ill-posed problem means small change in data can cause large change in results. So in order to overcome this problem, there is a technique called regularization. So it is used in finding a smooth surface through the scattered point of data, and it is mainly used in recovering 3D world from 2D images. So why regularization? We already know in order to select the best solution among the many possible solutions, we can go for regularization, and in order to have the best solution, I am going to add some penalty to enforce the smoothness. Okay, so yeah, energy function, that's what mentioned there, right? So ED plus lambda ES, the energy E is represented as energy function or functional. Low energy is good solution. So I am going to divide the energy function into smoothness as well as the data term. Now first we are going to see about the smoothness term. So smoothness is divided into, in this slide we are going to see about the smoothness ES term. The smoothness is divided into 1D derivative as well as 2D derivative. In 1D derivative, we have two things. One is slope penalty, another one is curvature penalty. So E1, E2 represents one first order derivative. The slope penalty represents first order derivative, and the curvature penalty represents second order derivative. It represents second order derivative. So f of x is nothing but the original function. So f of x represents the function, and this function is nothing but a slope at a point. Okay, a slope at a point, and this f of x is nothing but the derivative. It can also be written as f dash of x. So this part is derivative. Why we are taking square means, so larger scopes are penalized more. If we get more penalization, then the smoothness will be much good. Okay, so similarly for second order derivative, we are going to again integrate the first order one. So that is what second order derivative. In case of image processing, we will focus only on 2D penalties. In 2D case also we have first order derivative as well as second order derivative. Instead of x, we will consider x and y because it is 2D. So we have certain formulas just like above. So fx of x square, now it is x comma y, and again we have added a term for y also, fy square xy and dx dy, and here fx x square, right? So fx fy plus 2fx square into dx dy. This 2fx is to represent the rotational invariance, which means this represents x-axis, this represents y-axis, this is used to represent the diagonal. Okay, so when to use which order? Use first order for mild smoothing, preserving the edges moderately. We can use second order derivative if you want even smoother results and less visible artifacts. And sometimes you can combine them to balance both slope as well as curvature. If you want to balance the slope, you can go with 1D. If you want to balance the curvature, you can go with 2D. So these are the types of smoothness norms. First derivative norm is also called as a member model. The second derivative norm is also known as a thin plate spline. The blend of both first and second derivative norm is known as a thin plate spline under tension. Okay, so we can have a local weighting function which will be seen in discrete concept, I will tell you later, and it is known as a controlled continuity spline. A simple example is shown here. So here we have a surface with 9 data points of various scatters on a grid. So on applying the second order derivative, we have the transformation of the image from this to this. All the 9 points are blended to produce a surface like this. So second order controlled continuity thin plate spline interpolator. So it produces an image like this. So far we have seen about smoothness. Okay, so this is all about smoothness, 1D as well as 2D. In 1D we have seen first order, second order. In 2D also we have seen first order, second order. And now we are going to data term. Okay, so data term, for discrete data term we have certain formula, and for continuous data term we have some other formula. In case of discrete data term, we can take summation of a particular point I can be considered f of x comma y minus di the whole square, where di represents the observed data point. So the observed data point at the point I, the particular point I is summation, considered as for summation. For continuous noisy data, for that we have to take two values x comma y. So minus dx comma dy, this is the noisy term. This is the noisy image. So this represents continuous term, this represents the summation term. So on combining this, we are getting the formula, global energy function, ED plus lambda into ES. So lambda represents the parameter control. High lambda produces less structured data but produces good smoothness. Low lambda represents fits the data closely but with less smoothness. So this is all about energy formation. Energy formation contains two terms. One is data as well as smoothness. Now we are going to see discretization of degradation. Now in the previous term for smoothness we have considered only the integration part, right? So which means it can work only with the continuous data. But if you want to work with the discrete data, in general continuous data would cause infinity problem. So in order to minimize the continuous problem, this function is discretized on a regular grid. How to discretize? We can use some technique called finite element analysis. This can make the continuous data into grid of data, and we can perform the processing only inside the grid. Okay. Now again the same formula we are going to use in case of discretion also, ed plus lambda into es. Previously we have focused on continuous data. Now we are going to focus only on discrete data. Continuous means integration, discrete means summation. Okay. In previous cases we have focused only on integration, that is it can work only with the integration data. Now we are going to focus on discrete data because continuous can lead to the infinity problem. So first order derivative is considered here. We have so and so formula. I'll say what are these terms in an image, and the second order derivative also can be formed, but in addition to that we have to add some weights cx, cm, cy to this formula to make a good smoothness term. And discrete data energy ed can be represented with a weight, right? I have already mentioned about local weights. So when compared to previous data term, so this is the energy data term in continuous domain. So previously we have represented f of xy minus d of xy. Before that we have added a weight term. This w represents the local weight. Based on this local weight only, this image height and everything will be defined. Okay, so that is represented as w. So total discrete energy same, E equal to ed plus lambda into es. This results in the quadratic form of equation, that is x transpose ax minus 2 into x transpose b plus c. So where a is nothing but sparse. So on converting the continuous into discrete, we will result in a sparse linear system. Sparse linear system means most of the value are zeros. Most values in the matrices are zeros. So that is what a. X represents state vectors of unknowns. So a x equal to b. On multiplying the sparse matrix as well as the x data, we are resulting in b. That is what mentioned here, x transpose a into x minus 2x transpose b plus c. Okay, so this empty circle, a graphical model interpretation of first order regulation is shown in this figure. So the white circles are unknowns, f of ij, and the same diagonal, so I plus 1 comma j, and look at this is I comma j plus 1, and this point is j plus 1 and I plus 1. These points are unknown, and these are the weights we are going to consider as per the previous formula. That's what mentioned in the square. And this circle, shaded circles, the dark circles are the input data. Based on this, we can find the ED term. Okay, so the discrete energy minimization leads to the sparse linear system. The sparse linear system, I said most of the values are 0, which is not right. It can be solved efficiently using multi-grid methods. So what I said in the beginning, continuous data can be converted into discrete one. This discrete is nothing but formation of grid using finite element analysis. So instead of making a one grid, I can make a multi-grid methods in order to overcome the sparse problem. Or I can go with some other method like hierarchical preconditioning. So in general, this regularization can be applicable in the applications like HDR toner mapping, Poisson gradient domain blending, image colorization, and natural image mating. That's all about regularization technique in global optimization. In next part, we'll